All right, so today is the last class before the reading week. If you look at the semester calendar, let's just go over one more time, just to know what to expect. So the calendar says, so today is lecture number 11th, right here. So next Monday, either later Monday or maybe first thing on the Tuesday morning, I'll make sure you will get your assignment number 1 to work on. There will be some programming exercises over there. There will also be some theoretical exercises as well. So you can look forward to it. And then your test number 1 is going to be on the 27th, basically the second week after the reading week. I'll send you a guide very soon just to confirm about the coverage and also location and also time, etc. That's something I'll confirm. But you can definitely expect that everything that will cover all the way up to and including lecture 12 will be covered in that particular test. Okay, so just make sure you keep up with all the materials, and then I think tentatively during that tutorial session on the 24th, which will be the Friday, we can make that as a review session, maybe for your test 1. You can ask me any questions, maybe about the assignment solution, or maybe about some other lecture materials. That's something we can go over as well. All right? Any questions? All right, good. Okay, so today we definitely continue with the depth search, but before that, I want to go over also some another mathematical induction proof. It's definitely something very important for you to get right. But before that, let's do a recap on the materials from Monday. Okay, let's take a quick look. So we are here last Monday, 2 days ago. So we actually clarified about the simple cycle and also not simple cycle, right? Basically, just remember, a simple cycle simply means the cycle vertices should be in the beginning and also the end. Apart from that, whatever that's in the middle should be itself a simple path, meaning that there's no more cycle within. There's no nested cycle, let's put it that way. On the other hand, the not simple cycle will be, for example, you can see these two. Apart from that, you see a nested cycle, B and B, repeated again, right? That's not simple. So there are so many definitions that we have already introduced about the graph. You definitely want to make sure yourself are clear about how to distinguish between them, like the table that we actually went over last time. I can recap very briefly, but that's something you should really do during the reading week as well. Okay, we'll talk about the difference between forest and also trees. It is important to know that for forest, we assume it's undirected and also no cycle. So these are the only 2 requirements for the forest. Anything other than that is not required by a forest. For example, a forest does not need to be spanning, and also a forest does not need to be connected. So these 2 are the things you also want to pay attention to, right? When you study for the various categories of subgraph. And we talk about trees as well. So in the case of the tree, it's actually going to be a connected forest, basically. That's by the very definition, okay? Right here. Okay, so we talk about the trees somewhere. Okay, a connected forest. Okay, exactly. Okay, and then we'll also give you some example about being a forest but not a tree. All right, and then we'll talk about another specialized kind of tree, which is called spanning tree. That means the tree must be both connected, acyclic, and also spanning. Right? So these are all the terms you want to just recall exactly what they really mean, right? So that's something we already covered, so I may not repeat them. So please do pay attention to the detail. And we talk about basically some example of the spanning tree. And for spanning tree, you can see for each one of them, let's say for this example here. Number 1 is a tree. Because there's no cycle, it's acyclic. Number 2, you can see every node here, every pair of nodes has a path between them. For example, if I got A and F over here, I also got a single path between them, right? You can apply that for every possible pair of nodes, 2 nodes. And also it is spanning because you can see the subgraph contains all the nodes in the graph right here, right? It's a spanning. So that's why we call it a spanning tree. And we'll see later on how we can use some algorithm to compute the spanning tree, or minimum spanning tree to be more precise. But for spanning tree, we might just be able to compute it using depth first search. That's something I will try to remark either today or maybe on the Monday after the reading week. Today, I want to make sure I also cover one implementation strategy for graph in Java. Okay, that's something I want to do as well. So you can just get prepared for the minimum just to get assignment done, right? So there will be parts in your of your assignment number 1 about how to implement a graph using that strategy. Okay, I'll just talk about strategy very briefly. It's quite a simple one, but there's another 2 we're going to talk about after reading week. Right, so this is a table you want to get very familiar with. Okay, of course there will be some memorization, unavoidably. So you're going to make sure you understand about each term over here. We spoke about exactly what kind of criteria they will satisfy. Of course, for your tests and also for the exam, there'll be no data sheets allowed. So you really have to know about the definitions, right? Not just the graph, but also the trees, high balance property, how you can do rotation, and also other things, right? So you want to make sure everything is actually clear to you. All right, so we talk about subgraph, spanning subgraph, forest, tree, and also spanning tree. So these are the terms we have mentioned so far. They're very important, okay? I'll let you double check the table. And then we did some visual exercise about a spanning tree. So given this particular graph, we want to find a subgraph that happens to be a spanning tree. And it turns out this is a spanning tree. And we talk about A here, and also B here. Each one of them is not a spanning tree. Of course, we explain why not, right? You also want to revisit the reason and see, okay? So that's also important. And then we started talking about graph traversal, okay? So there are various applications that we actually can use to solve using graph traversal. Some of them can be done using depth first search, but some of them cannot be right away. For example, getting the shortest path. You cannot really do it right away using a depth first search. Beg your pardon. And we're going to learn about another graph traversal later, shortly after the reading week. It's called breadth first search. It's a different flavor of the graph traversal, in which case you will be able to find a minimum, like a shortest path using the breadth first search. Okay, we'll get there. Okay. I think most likely I'll try to make this as a remark maybe after the reading week. So once you get a little bit more exposure to doing the exercise on the depth first search, so we can see a little bit more. Okay. Okay, so and then this is the only example we did on Monday, just about how you can do a depth first search on a tree. Okay, you can see this particular graph over here happens to be just a tree. Okay, you can see number 1, it is connected between every 2 nodes. You do have a path. And also, there's no cycle there. And also, it is also connected, right? As we said, every 2 nodes have a path. And we try to do the depth first search from there. And if the graph you're given happens to be a tree, and then the depth first search you will do happen to be just like a pre-order traversal that we learned from 2101. So what you should do is review about how the pre-order traversal is done, and then try to see why. Just try to see how the pre-order traversal just corresponds to how you do the depth first search using a stack. Right? You can review about the process that we did on Monday. But today I'm going to do more examples just to show to you how you can use a stack to really complete the depth first search. Okay? We don't see any code just yet. There might be some programming exercise I can give to you as well for assignment number 1. Okay? Okay, and we spoke about in order to really get the depth first search to work, you have to somehow annotate or mark both the vertices and also edges. Okay? For vertices, there are only 2 things you're going to mark. Either a particular vertex is not visited in the beginning, or it has been visited. Ultimately, for the depth first search, we got to make sure we visit every vertex in the graph. Right? So everything is going to be turned into green. So my color convention will be the red or pink means the node is unvisited. And the green one here, it means it has been visited. Right? So you should really turn from unvisited to visited. That's the case for the vertex. On the other hand, for edge, so there are 3 possible statuses, 3 possible stages for the edges. In the beginning, we say that, let me put it here. Just to summarize quickly, okay? So when we talk about depth first search, DFS, and we say that for each vertex is either unvisited or it is visited. Only these 2 possible states for the vertex. But for each edge, you got 3 possible values. For each edge, initially it is unmarked, or you can say unexplored. And then as soon as it is marked or explored, there are two possible values. Either it's discovery edge or it's a back edge. Discovery edge. That means the edge leading to some unvisited node or vertex. If the edge you're looking at is actually leading you to some vertex that has not been visited yet, then that'll be discovery. You're discovering something new. That's why the name. Go ahead. Oh, thank you so much. You saved everybody. Yeah, thank you. Yeah. Okay. Yeah. I should do that. Now, guys, whenever you see anything like that on the top, please do let me know. Sometimes I do forget. Okay. Yeah, you don't really want that to happen, you know. Okay, good. Okay, we're good. Okay, thank you. Okay, let's now continue. So if the edge is going to lead you to something that has not been visited so far, so it's going to be discovery. On the other hand, if it's going to lead you to something that's already visited, it's called back edge. Okay, let me just make some space. There we go. Put it here. It's called back edge. So leading to some visited vertex. Okay, we'll reinforce about these two edges again today. We'll see more examples. And then I'll give you some complicated one, maybe for the assignments. You can definitely practice. Okay. So for vertices, you got two possible annotations, and for edges, you got three possible different states. Okay? And that's basically what we said last time. Okay? Any questions so far? We're good? Okay. So to start with, for today, I would like to do one mathematical induction with all of you. But before that, I want to do some property check as well. Okay? So the slides I'm referring to, let me just tell you. I'm referring to slide number 23, okay? So this one here is kind of interesting property. We're saying that given that your subgraph is a particular category, for example, spanning tree, or it can be a forest, or it can be a connected subgraph, etc. Given that you know the structure of your subgraph, you can actually get some conclusion saying that what should be the relationship between the number of vertices and also the number of edges. Okay, that's what the property would say, okay? So this will be the list of properties. We got 4 of them. So we talk about spanning tree, we talk about forest, we talk about the subgraph being connected, and also we talk about the graph being cyclic, containing a cycle. I'm gonna just go over each one of them, just give you some example just to see how the property can be understood, first of all. And then I'll show you the mathematical induction for one of them. And of course, you should really try to practice using mathematical induction to prove others. Okay, they'll be done in a very similar way. Okay, so let's now start with the first. Let's just go over the property quickly. Okay. Okay, let's now. Okay, how do we understand property first of all? Okay, let me just use one of them as an example. Just watch out very carefully about the language over here, because somehow we use the natural language like English to specify it's not exactly formal. Okay? So when we say we got n vertices, we got n edges. So here we say n, the number of edges, is equal to the number of vertices minus 1. We say this will be the case if the subgraph is a spanning tree. But now how do you understand this exactly formally? Okay, I'll put it down here. Okay, just for the first one. The other 3 will be understood, should be understood in a similar way. This one is saying this. If I know that G is a spanning tree, that implies n equals n minus 1. However, this property here doesn't say if and only if, which means if I know that this is the case, does that backward imply this is the case? Not necessarily, okay? Think about that, right? That's one thing I want you to be aware, okay? So what I want you to also think about, we can do some exercise as well. I can put that in the assignment for you to think about. So here, if I go back this way here, put a question mark, be suspicious. Okay? The property actually is formulated this way for a reason. Otherwise, we should have said if and only if, right? All right, let's now focus on the property. Okay? Let's just see some example. Okay? So now I'm just going to create a different subgraph, and then we're going to go over to see if the property will actually be valid. Okay, let me look at my notes. Sorry, bear with me. Okay, there we go. Okay, let's see the first one. Let me give you one spanning tree. Let's say this, the subgraph here is going to cover all the nodes. So let's say I got, okay, let me just put it, let me color the nodes. That'll be a little bit faster for me. So let's say I got A, oh, sorry, this one here. Let's say I got A, B, C, D, E, and F, right? Let's say I got all the vertices in the subgraph. And then I got the following edges. I want to create a spanning tree, basically. Let's say for the edges, I'm going to get one here, one here, one here, one here, and one here. Would you agree it's a spanning tree? It is, right? Okay, you can double check the definition, but it's a spanning tree. So now, given that this subgraph here is a spanning tree, it's spanning and also it's a tree. So now, let's now double check the property. According to the property over here, if you think about the number of vertices right here, A, B, C, D, E, F, 6. How about the number of edges? 1, 2, 3, 4, and 5, which is exactly equal to the number of vertices minus 1. So that one satisfies this property here, right? Because we said that the number of edges is actually E, and the number of vertices is V here, right? So this property here is satisfied for this particular example, but I'm going to prove it. I'll prove this one for you, okay, together. Okay, we'll do that. Let's do another example here. Let's say we want to have a forest, and the property says that if I have a subgraph that's a forest, then this inequality can hold. Let's just use one as an example. So the forest, we know that it does not need to be spanning, right? It can be spanning, but does not need to be connected. Let me just put it down here. Okay, so what I will have is, first of all, let's see, we got a spanning subgraph. So I'm going to get A, B, C, D, E, F. Okay, and then what about edges? Let me give you the edges as follows. One here, one here, one here, and one here. All right, so this one here is a forest, but it's not a tree because it's not connected. Why is it not connected? Because you can see that between a pair of vertices, for example, E and F, there's no path. It's not connected. All right, I'll write it down for you. So this one here is actually spanning but not connected. But not connected. Definitely not the case. Okay? And then let's now check the number of vertices and edges. Number of vertices will be A, B, C, D, E, F, still 6. The number of edges over here is 1, 2, 3, and 4. Right? You can see 4 here is less than or equal to the number of vertices minus 1. Right? You can see that inequality over there. Right? If you check that inequality here, so 6 minus 1 will be 5. So I'm just getting something even smaller, 4. Just one example. Okay? Any question about this? Okay, good. And the next one, being connected. It should be at least n minus 1. Should be, all right? So now for connected, why don't we do the following, okay? So let's say we can still have, right here. In order to be connected, let's talk about a graph like this, subgraph. Let's say I got A here, and then I got B here, and then I got C here, I got E here, I got D here. Let's say for this particular subgraph, I'm not making that spanning, meaning that I'm not covering all the vertices, but that's okay. It's only about connected, right? And then I'm just going to include 1, 2, 3, and 4. Okay? So this one here is connected, but it's not spanning. So this one here is connected, but not spanning. Okay, you can do a similar check, and it is going to satisfy exactly this particular equation. And this one is interesting. It's saying that your number of edges has some minimum over here, exactly n minus 1. That means you can keep adding edges if you want to. For example, I can also choose to add one more edge if I want to. If I try to add one more edge, for example here, is it still connected? It is. I'm just adding more connection. It's already connected, just even more connected, equally connected actually. Connected doesn't really mean you cannot have a cycle. Okay? So when I say connected, that means may or may not have a cycle. May or may not have cycles. All right? That's important for you to see. All right? The final one, in order to be a cycle, that means you must have at least n edges. That means the number of vertices and number of edges should be at least the same. Okay? So now let's just do one more graph. Okay? This one will be the most important one. You want to look at basically these two together. Look at this one here, and also this one here. The first one here and the last one. The spanning tree and also a cycle. You can see that, okay? So let's now color that. So let's say I got A, B, C, D, E, F, all right? You can, over there it says that it should be larger than or equal to n. Let's make it not exactly equal. So let's make it, let's say 1, 2, 3. Number of vertices over here is 1, 2, 3, 4, 5, and 6. Let me make it exactly n minus 1. 3, 4, and 5. Right here, I have a spanning tree because that's exactly n minus 1. In order to have a cycle, I need to have at least one more. By adding just one more edge, it's guaranteed. Okay? So this edge is telling me over here, more edges than just n minus 1. So that means at least n edges. That's going to guarantee you have a cycle. You've got exactly n minus 1, it's the characteristic of a spanning tree. But if you got more than n minus 1, you guarantee to have a cycle. Yeah?
Can you have a cycle and then a bunch of disconnected vertices?
It's possible.
Wouldn't that not follow this property?
Oh, sorry, which one? You mean the last example?
Yeah. Right.
Okay, sure. The last example there, yeah, I'm just giving you one example here, right? So if you think about, let's say, this particular subgraph. So I got 1, 2, 3, 4, 5, 6 vertices. And then I got 1, 2, 3, 4, 5, 6 edges. So that's exactly the equal part. So I have a cycle.
What if you don't have the edge from input path?
My point was more like, imagine like if you delete the edge from A to B and from E to F, but you keep the rest of the graph graph the same? We have a cycle between.
Very good question. Okay, I know exactly what you're asking. So this boils down into about whether the implication here is one way or two ways. We're saying that if you got a cycle, that implies this must be true. However, having this true, or sometimes not having this true, might still give you a cycle.
Well, if you delete those two paths right now, the graph would still have a cycle. There's a cycle from A to E, E to D, D to C, and C to A. There's still that cycle.
Okay, let me create exactly what you're saying. Let me double check. So which one do you want to get rid of?
A to B.
A to B? Like that?
Yeah, and then get rid of E to F.
Get rid of E to F.
Right now, we have a cycle in our graph, but we have more vertices than edges.
Okay, that's one.
I can't read. I mixed them up. I thought, never mind. I mixed it.
So let's say this one here, okay. This one here, the number of vertices is exactly equal to 1, 2, 3, 4, 5, 6. And the number of edges right here is 1, 2, 3, 4. You do have a cycle there, and then, yeah, you actually got number of, okay, that's interesting. There might be some missing assumption
Will
here.
we apply when it's connected?
It might be. Okay. Let me put this as a question mark. I'll look into this. Interesting. Okay, I'll get back to you on this. Okay. There might be some missing assumption I didn't mention in the property. I'll double check. Good. Okay, thank you. Good. I think the overall, we just have to know this. Well, I'll come back to this for clarification. But let's now take a look at this one here. If it's a spanning tree, then this must be the case. Let's see how we can prove it mathematically. Okay, good. Right, the way we're going to prove it is by mathematical induction. And let me just highlight that one there. This is the one we want to prove. Okay? If it's a spanning tree, then it will be this equality here. Okay? Let's talk about base cases. So we're going to do mathematical induction. So we're going to say mathematical induction on the number of vertices. Okay? And here we say the number of vertices should be at least one, not empty graph. Okay? We're not considering that. All right, let's talk about base cases. So we're going to talk about vertices, number of vertices being 1 or 2 or 3. You can just do a few, or just do a couple. Okay, let's do 3. So base cases. Okay, we talk about spanning trees. With, let's say, 1, 2, or 3 vertices. Let's see, based on these spanning trees, is the property here going to hold? Right? We can easily show that. Okay? Let's say when the number of vertices is exactly equal to 1, right? And this one here, it's a spanning tree automatically without any edges. Okay? In this case, m is exactly equal to 0, which is 1 minus 1. And when we actually got n equals 2, we got 2 vertices. And in that way, to really create a spanning tree, well, basically, like that. Okay? And the m is just equal to 1. Also, n minus 1. One more. If I got n is equal to 3, if I got 3 nodes, or 3 vertices in the graph, for me to create a spanning tree, I got 1 here, and also I got 1 here. Okay, you cannot create any. You cannot add another edge. In that case, you will have a cycle. That's not spanning tree anymore. So that will be n equals 2. So this property here actually holds in the base cases. Okay, and let's make our inductive hypothesis. Okay, I'll write it down here, which we're going to use to rewrite the equation when we talk about something that's larger. Okay, so this is our inductive hypothesis. We say that G is a spanning tree. That means for G, if we got a number of vertices, let's say it is equal to n, and also number of edges is equal to m, it's going to satisfy exactly this property, such that m is equal to m minus 1. Okay, that's what we assume. And you can also say the v here should be larger than, let's say, 3, since we already covered the base cases. Okay, that's the inductive hypothesis. We're going to use it very soon. Okay, so let me just highlight it. Okay, inductive hypothesis. Okay. So what we should do now is let's try to consider a strictly larger graph. Okay. Again, we're going to use that cloud approach. Okay. Step number 3. Let's say I have a spanning tree right here, which I assume. Like that. Okay. So this is a spanning tree. Where we got number of vertices is equal to n, number of edges is equal to n. And I know that it's going to be exactly equal to n minus 1. Okay, I will just write that. N minus 1. Okay, like that. So this is, of course, based on our inductive hypothesis. That's something I know pretty well. What I want to create now is a strictly larger graph by adding one node, one vertex to it. Okay, so if I say I want to add a new vertex to it, right here. Now, what I want to do accordingly is, how can I create a strictly larger spanning tree for this new graph? How would I do that? Add a node? Well, the node is here, right? Connect the node. Which node? The new one to where? Some old node, right? Arbitrary node, right? Yeah, exactly. Doesn't really matter, exactly. Okay. So that means I'm going to pick a node. I'll write it down as a part of the step. Choose a node here, because we know the cloud here got at least 3 nodes, at least. So I can choose any one of them. Okay. Choose a node from the cloud and then connect them. This will make it a spanning tree for the strictly larger graph. Okay. So think about right here, this part over here, including a new node, is really a spanning tree. That one there is really a spanning tree with the number of vertices equal to n plus 1. And the plus 1 is really the new node I just added right here. Okay, so far so good. What we need to now argue is about the number of edges. Let's see exactly, right? So let's now start the equation. So let me call that this part over here, you can think about as a v prime. Prime here just means the new graph. So v prime and e prime are the number of vertices and edges for the new graph. Okay, you can think about this is the v prime. Okay, let's now talk about e prime. E prime. So this will be the number of edges in the larger spanning tree. All right. Let's now try to think about how many edges are there. Basically, it would be however many edges we have in this smaller spanning tree, plus 1, according to the diagram, right? That's going to be basically E here plus 1. So this part here is the number of edges in the smaller spanning tree. How many are there in the original one? According to inductive hypothesis, n minus 1, right? So that's where we're going to use it, all right? So here we're going to say equal to, based on the inductive hypothesis, is going to be n minus 1, right? N minus 1, and then plus 1. And that one there is going to give us just n. And then we know that v prime over here is n plus 1. So we know that it's exactly equal to v prime minus 1. So what we have shown is this. We have shown that the number of edges in this strictly larger spanning tree is exactly equal to the number of vertices in that strictly larger spanning tree minus 1. That's what we have shown. And to really show that, we have to use the inductive hypothesis right here, okay, which is right here. It's a very simple proof, actually, but in order to really do it, you really have to show this critical step about how you can construct a strictly larger spanning tree. That's pretty similar to how we did it for the simple graph, if you remember, about the degrees earlier. All right, any questions? Go ahead.
Not so much about the proof itself.
Uh-huh.
Not like in the math classes, they're very picky about the formatting, but
Yeah.
you use a lot of like just writing words and drawing pretty pictures.
Uh-huh.
If we do that on the test, is that okay?
Of course, you cannot really do colors, right? Unless you want to bring highlighter, right? Okay, good question. I would say in the test, of course, you have to, well, for you to really, okay, let's say in the test, what will be acceptable? Number one, you have to show the very clear 3 steps, right? Step number 1, you have to show the base cases. And I think very naturally, if you want to prove property about graph, you have to somehow draw. You have to really convince. Otherwise, sometimes if you only simply write in words, it's very difficult to see what's happening here. So don't be too hesitant about drawing graph, when things can help, right? This is okay. And I would say this one here is also quite important for you to really show how you can go from something that you can assume based on the inductive hypothesis to something strictly larger. That's also important. I think that this is the part that's going to be not really visual, not very pretty. That's really the part you're going to show mathematically, right? I would say this one here is important for us to get convinced you about your intuition of building the graph that's strictly larger. And this is the part you can show that you can really apply the inductive hypothesis and show that equation will actually work. So both parts are important. Does that kind of answer your question? Yeah. Good. Okay, I'll give you guys maybe more proof questions, maybe in the assignments. You can give it a try. All right. All right, so we are just about halfway. Why don't we take a short break by taking attendance? After the break, I would like to do maybe 1 or 2 more examples about the depth first search, and then I will talk about how you can implement graph by using some strategy. All right? All right. Okay, so let's now do examples on depth first search. Okay. Okay, I got actually 1, 2, 3, 4, and 5 examples. Okay, I'll only do one of them, but this one here, I'll leave that as an assignment question for you. Okay, so that one there also, you can give it a try, and also when I release the solution, you can also compare. But let's now do one thing. That should be good enough for you to see all the principles you're supposed to know. Okay. Every time, I think the most important thing you should really be informed is about, for each vertex, number 1, where does the DFS start from? Okay, so number 1 should be start vertex of the DFS. And let's say we start from A. Okay? May not be A, could be some other vertex. Okay? And number 2 is about what's going to be the order of visiting the adjacent vertices. The order of visiting adjacent vertices. Okay, so these two things are very important, and usually I will specify up at front for the question. Okay, so these two. All right. So for this particular example here, we start with A, and the assumption is for adjacent vertices, we're going to follow the alphabetic order. Okay, in this case, okay, we'll see some variants of that. So that's going to result in some different annotation for the depth first search. Okay, for this one here, so what does that really mean? I would suggest, depends on how comfortable you might feel, but for this very first example here, just to be very systematic, along with the stack, I'm also going to give you some table over here, just to remind us about the order. Okay, so let's do the following. So let's draw a table right here. So the table here is going to talk about the different adjacent vertices for each vertex. So here we got A, B, C, D, E. A, B, C, D, and E. And they have their adjacent vertices. So when I say about the order of adjacent vertices, at the same time really talking about how what should be the order of visiting the incident edges, really the same thing. When I say I'm going to visit adjacent vertex B, I'm really visiting this particular adjacent like incident edge, really the same thing, right? Just talk about either edge or vertex, okay? So now you can see for A here has a degree 1, 2, 3, 4. That means I got 4 adjacent vertices, B, C, D, E. So that'll be the alphabetic order, right? So it's going to be in this order. B, C, D, and E. What about for B? For B here, it got degree 2. It's going to be A and C. And then what about vertex C? Also got degree 4. So that means it got B, A, D, E. So that should be A, B, D, and E, right? In this order, alphabetic, okay? And for D here, we got degree 2, A and C. And for E here, it's also degree 2, also A and C. So that'll be the order, okay? We only visit that particular vertex if that's unvisited. If that vertex is already visited, the edge is going to be a back edge, as we'll see. Okay, we're going to go over thoroughly. Okay, along the way, we're also going to have a stack right here. Oh, sorry, right here. A stack. Okay. So, of course, there might be different ways I can ask the questions. I might just say, given this graph, so now do a depth first search, and then I might just ask you to give me the discovery edges in the result. I might ask you to give me all the back edges in the result. Or I might simply ask you to tell me what's the order of pushing the vertices into the stack. And also, what's the order of popping off the vertices from the stack, right? So there are different questions I can ask, okay? So I'll write it down, okay? So questions could be, just an example. It could be, give me all the discovery edges. Or it could be, give me all the back edges. Or give me the order in which the vertices got pushed onto the stack. Let's say the order of pushing vertices. And symmetrically, the order of popping off the vertices. Okay, so these are just 4 example questions I can ask. Okay. Okay, let's now go with the first one. A is going to be the starting vertex. So that one there, well, let's say initially, right? Initially, everything should be unvisited. Let me just follow the same color convention as before. Okay, so we got A here, B here, C here, D here, and E here. So in the beginning, all the vertices are unvisited. Okay? And also all the edges are unmarked. or unexplored. Okay, so let's say I'm going to visit the first one. So I'm simply going to put A to the stack. And then at the same time, A here is going to be visited. Okay, sorry, let me just go here. Okay, good. And that one there is going to be visited. Right here. Change that to be green. Okay? So now in A here, I need to now make a decision about visiting its neighbor. Okay? According to the order I just specified, I should really go to B first. Right? So I should go to B. Okay? So I'm going to push B. You can see B here is actually unvisited, which is good. I'm discovering something that's unvisited. So I'll push B to the stack. Okay? So in that way, I'm going to mark this one here as visited. At the same time, it is important to mark the edge as discovery edge. Okay, I'm just going to go this way. Discovery edge. Okay, just remember here, if I got an edge like that, versus if I got an edge like that. So they're different. Okay? So this is the discovery edge. Okay, let me put it along here. Discovery edge versus back edge. Okay, like that. So now B is there. And once B is there, we can get rid of it. Okay, so I can simply remove it. Okay, so that means when I ever get backtracked to A, I don't have to worry about visiting B anymore. I don't have to, because that one there is already a discovery edge. So now I'm now in B. So B is visited, right here. Okay, so now according to the order, I should first of all go to A, here. But A is already, going back to A, this edge is already marked. I don't need to worry about it. Okay, so I go directly to C. Okay, so for the first one, I'm just going to say here, A here is already marked. So I don't have to worry about it. So I go to C. And when I go to C, it's going to be another discovery edge. Okay, and then that one there is going to be C. C here. Okay, so that means I'm going to push the C to the stack. And this one here is removed. What that means is, as far as C is concerned, we have already handled both of its adjacent vertices. Okay, both of them are just discovery edges. Okay. Okay, let's now go to C. And for C here, let's see what's going to happen. So for C here, we first of all go to A, right? So now you can see if I go to A, I'm basically visiting something that's already visited. So that one is a different edge. It's a back edge. Okay, so now A is done. And then the next one I should really visit is B. So go from C to B, and that particular edge is already discovery. So I also don't need to worry about it. It's also marked. And then from C to D, over here, that one there should be discovery, right? Okay, so I'm going to go from C to D. Oh, sorry, C to D over here, and then I'll turn that into a visited node right here. Okay, I should push the D onto the stack. And D here should be gone, right, from C. Yeah, since I'm illustrating, so a little bit slow, but when you practice that, of course, you can be much faster. Okay. All right, let's now go to D. So now we are talking about D here. And first of all, we should go to A. A here is actually something already visited. What should that be? Back edge. What should we skip? Back edge, right? Because this edge here is not marked just yet. Okay. So it's going to be another back edge. right here. Okay, another one. Okay, so D to A right here is gone. What about D to C? D to C, we also don't need to worry about it because that one there is already marked as discovery. Okay, that's also already marked. So you can see that as far as D is concerned, we have already handled all the neighbors, both neighbors. We have handled this one here, we have handled this one here. So D can now be, is completely done. That's the very first one, that's completely done. So we can remove it from the stack. All right? So we can now remove D here from the stack. What will be the next one to handle? C. So we go to C here. If you look at C here, we have already handled A, B, and D. What's really left is E. Right? So now what should that be? Discovery edge. Right? It's going to be a discovery edge. Going to here, and then I'm going to mark that vertex to be visited. Okay, so I'm just going to go for E right here. Okay, so now for C here, E is gone. All right, and let's say for E, what should we do? Yeah, thank you. Yeah, I agree. Yes, back edge. Good, thank you. So you can see the back edge will be right here. Right here. Back edge. So that will be for A. What about E to C? Skip, because it's marked already. Okay, you guys pretty much got the idea. Let's be complete. Let's finish everything. And then I'll show you what to do with the other example. All right, so now as far as E is concerned, we are now done. So pop it off from the stack. And now for C. C here is also done with everything, right? You can see everything here is done. So C can also be popped off. So now we talk about B. B is also done, everything. And then we go back to A. We still got C, D, and E. Do we do anything? Not really, because you can see go to C, go to D, go to E. All the edges have been already marked as back edges, so we don't need to worry about them. All right? So you can think about C is already marked, and D is already marked. And also E here is also already marked. Okay? And then we can pop off A. Now the stack is empty. So now the depth first search is done. All right? So this will be the discovery edges. You can see this, 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 and this. And this one here happens to be a spanning tree. And then, since we got at least one back edge, that also means we actually got at least a cycle in the graph. Okay? So there will be some remarks I would like to make maybe on the Monday when we come back from the reading week. So once you have done some depth first search, there are many questions you can actually answer using a depth first search. That's something I want you to also think about maybe when you do the study during the reading week. Okay? Let me write down the remark, and then I'll tell you what to do with others. So all the discovery edges happen to form a spanning tree. Number one. And number two, there is at least one back edge. That means the graph that we perform the depth first search on is cyclic. It contains at least a cycle. Right? So these are two observations we can make. All right. I still got three more, basically the same diagram. Okay. Let's say we always start from A, but now I want to modify the order a little bit. Okay. That's something you can give a try. It's going to give you different annotations. So here we're saying we are basically doing alphabetic order, except that AC must be visited first. That's more like an exception you want to give more precedence to. Okay? I'll just draw the table very quickly for you, and then you can do the rest. So here, what we have is, we still have our A, B, C, D, and E. And we got adjacent vertices. So now for A, if we simply follow alphabetically, so let's say we start from A, it will be B, C, D, E. B, C, D, E. But we say that AC must be visited first, right? So it's going to be C, B, D, E. So this is some exceptional rule we apply, right? So that's going to make a difference, okay? And then for B here, we just got A and C. And for C here, it's going to be B, A, B, D, E. And for D here, it's going to be A and C. And for E here, it's going to be A and C, right? So basically, we just change the order right here, okay? And try to see what the final annotated graph is going to look like after that first search. Okay, think about it. It's going to be different, I can tell you. Okay. All right, you got similar example there. You can also try. Another one, the exception is we do AD first. Another one, we do AE first. All right, question, please.
Sorry, in the example that you did, was D the first one to get hot?
I believe so. Okay, I don't.
Could you just say the order?
Yeah, how about this? Let me put that maybe when I release the notes. I'll put the answer. Yes, good. Okay, yeah. I didn't really keep track for this example, but I should. Okay. No, it's a fair question. So for these two questions here, I'll make sure I include the notes. Okay. Let me revisit the process, and I'll put the answer there. Yes, exactly. Good. All right, so try that. And then, guys, this one here is going to be fun. Okay? You can see it's a much more complicated graph. And then we say that, let's say we start with A, and then try to do depth first search and see how you can mark the discovery and also back edges. And I'll make this one here like an assignment question for you to try it out. Okay? And I'll also give you a solution. Okay? All right, one more thing I want to talk about for today. Okay? I want to talk about how you can implement a graph in Java. So there are 3 strategies in total that we're going to go over in the course. So today, just the first one. Okay? And that one there would be enough to already let you do some programming assignments already, which is going to be fun. Okay? So let me go over some background here. Okay? So we're going to start with slides right here. Okay? Okay, this one here. Okay, it's going to start from slide 33. It's only about 4 or 5 slides of the code. It just gives you the skeleton or some basis. And then in the actual assignment, I'm going to give you some example methods you can try to implement on this particular strategy. Okay, so the skeleton code you will definitely be given in the assignment and also in the test 2 classes. Okay, let me go over this. So remember, you learned about doubly linked node and doubly linked list in 2101. Okay, let's take a look. Just brush up the mind. Okay, we got doubly linked node right here. Let me just highlight it. Doubly linked node right here. Okay, so it's generic E, which can be instantiated to any elements, integer, string, person, any object. Each node stores some reference called element. And then we maintain, because it's doubly linked, you maintain a reference to the previous, maintain a reference to the next. Previous, and also next. So previous over here, and then next. I'll visualize some code example with you, just in one moment. So this one here, we got also doubly linked node right here, and also doubly linked node right here. Okay, refer to itself. And then when you first create some doubly linked node objects, you have to pass the elements, pass the previous, and pass the next. Okay, that's something you will see in the assignment code example. Okay, very simple class. Okay, and there will also be some setters and getters. Let's say set the predecessor, set the next, or get a predecessor, get the next, etc. It's very standard getters and setters. Okay, so that's about a node. And then we got a doubly linked list class as well. And for that one there, doubly linked list. All right. And if you recall, from 2101, for each doubly linked list, we're going to maintain 2 so-called guard nodes or sentinel nodes. It's called header here and also trailer. Header here, and also trailer here. So these two nodes are always there. So when you actually talk about an empty list, so if you have an empty doubly linked list, it will look something like this. So the list itself is referring to some objects. So doubly linked list at the runtime. And then you have some attribute called size. And the size will just be 0. And then you got header and you got trailer. Header. And then, okay, let me write better. You got header. And also you got trailer. Think about the header and trailer always exist in the list, even when the list is empty. So the header is actually going to point to some doubly linked node. Okay. And the trailer is also going to point to some doubly linked node, like that. And the header and trailer simply point to each other. Okay. So they will be actually the different references. I'll talk about it. Just give me a moment. Remember, for each doubly linked node, we store the elements, and we store the previous, and we store the next over here, right? For both header and trailer, their element part, I would say E, is always null. They don't store any meaningful data. Element here is also null. And then we got previous and next. Okay, the previous for the header is null. The next of the trailer is always null. Okay, and then we actually got the previous of the trailer points to the header. So this is a previous reference. And also the next reference of the header points to the trailer. Okay, you will see some example tests in the assignment. Okay, but I just want to visualize to you. So just remember, for our context, the header and trailer always exist in the doubly linked list as two nodes. Okay, it's going to make insertion and removal easier for us. I'll just give you one example here. Let's say we got a doubly linked list, and we got size, we got header, we got trailer. Let's say we got a particular method here called remove. We basically say, given some reference of a node, and we assume that the node actually exists in the list. Okay, I'll write it down. So the node here, so the assumption is, the node here, the assumption is, the node exists in the list. You're trying to remove some existing node. And this turns out to be a big O of 1, constant amount of time for running time. And this turns out to be big O of 1. And this remove method here is very important because you will see that in order to build a graph out of some linked list, if you want to remove some vertex, if you want to remove some edge, it's only going to take constant amount of time. We'll see. Okay, let's try to visualize what's happening here for the remove method. Okay. So what we have is, we have the remove method here. Okay, let's just follow faithfully line by line. Okay, let me just highlight it. So we got 1 here, we got 2, we got 3, we got 4, we got 5, we got 6, we got 7. Okay, and the node, the parameter is, think about the node here. It's just somewhere in the list. You can think about the node here. So the goal is, I want to remove this particular node from the list. But how do I do that? Conceptually, you simply just want to make sure its predecessor is going to point to here. Its successor is going to point here. So this one here is completely garbage collected. That's what we want to set up. But let's see exactly how to do that. Okay? So there'll be certain steps you got to follow. Okay? Let's go one by one. So for number 1, let's now have a local variable called predecessor. So the predecessor is going to be the node.previous. So the node over here, .previous, is actually going to be the predecessor. So I call this one here the predecessor. Right? Number two, I'm going to create another local variable called successor. It's going to be node.getSuccessor. Okay? So node.getSuccessor, which will be the next one. So this will be the successor. Okay? So think about this is number one, and this is number two. All right? Number three, I'm going to do some reference setting. Predecessor.setNext will be successor. So predecessor.setNext, rather than pointing to here, is going to point to the successor right here. Okay, so this will be number three. Number four will be very similar. Successor.setPrevious will be predecessor. So successor right here, the previous, rather than pointing to here, is actually going to point to the predecessor right here. Okay, so this will be number four. Okay, we're almost done. And then number five, we're going to set the next of the node to be null. So that one there is actually going to, the node, if you remember, the node is here. The set next to be null. So this one here is number five. And then the node that set previous will be null. Node that set previous right here is going to be pointing to null. At the same time, you also try to decrement the size because we're removing one node, right? So these are basically what you learned from 2101. I just want to review very quickly about the essence of manipulating doubly linked node. Okay? So there will be some methods I can give you to practice in the assignments. Okay? Okay, let's see how this can be incorporated into implementing graph. That's why we want to review this. Okay, let's now do that quickly. So first of all, let me just go back here. So we just talked about the doubly linked node and doubly linked list. So there will be two classes. Okay, let me show to you. Let me go this way here. Let's go one by one. We have a class called vertex. And the vertex itself stores some data elements. And then we just set the element to be that particular element. Simple class. We got another class called edge. Okay? The edge over here is going to store itself some elements. And then the v here corresponds to what can be stored in the vertex. That's why we pass the v, just generic parameter. And then for each edge, we basically got origin and destination. So you can think about for each edge, we actually got origin. Okay, let me just write it down here. So we got origin and also destination. Destination, right? So these are the two, origin and destination. And then when we first create a new edge object, we simply set the element accordingly, right? So these are the two classes, very simple. And the implementation strategy that we're talking about is called edge list. So this is a strategy we're going to learn first. So this is strategy number one we're going to learn about implementing a graph. There will be three in total, but for today, just one, edge list. We have a special class, like a subclass, called edge list vertex. And also we got some edge list edge. Okay, just to say something specific about this particular implementation. Okay, and then notice that here. Okay, so think about this reference over here. It's about pointing something to the position. Okay, I'll just maybe highlight it. So this will be the position in the vertex list. I'll show you one diagram in just one moment. And also here, this will be the position in the edge list. Position in the list of edges. Okay? And one more class, and then we can see some visualization. And the final graph class we want to have is called edge list graph. Okay? V is the data type for the vertex, and E is for the data type of edge. We got two parameters over here. We got two doubly linked lists. Doubly linked list number 1 and doubly linked list number 2. Okay? One is called vertices, the other one is called edges. And also we have a Boolean flag to tell whether or not the graph is directed. Very straightforward. True for directed, false for undirected. And then the constructor here should be very straightforward. You simply create empty list of vertices and edges to begin with, just empty graph. Okay? That's about the classes that you will be given. And let's now do one more thing to visualize, and we're done. Okay? Let's say we have a graph here. I'll try to explain to you how exactly to see the correspondence in the diagram. Okay? So we have 1, 2, 3, 4, 4 vertices. And also we got 1, 2, 3, 4, 4 edges. All right? That's what we have. And this visualization here, let's now go over very quickly. Okay? But I'll annotate for you. Okay? Let's start with the list of vertices. So this part here, A, B, C, D, simply correspond to the A, B, C, D here. A, B, C, and D here. So these are the list of vertices right here. Okay? These are, oh, sorry, beg your pardon, it's not exactly that. Okay, let me just say that. So these are the vertex objects. These are some individual objects of type edge list vertex. Right here. Okay, edge list vertex. And similarly, we also have the edge objects. These 4. Okay, think about we have 1, 2, 3, 4. They correspond to 1, 2, 3, 4. 4 edges. Okay, so these are the objects of type edge list edge. So these are the objects of type edge list edge. Okay, we got individual object first. And then the next two are the attributes for the edge list graph. So this one here, and also this one here. Okay, this one here is the list of vertices. And this really corresponds to the vertices right here in the graph. And this one here is the list of edges, this list. List of edges. And that one there corresponds to the edges right here. Okay, one more thing to show to you that's also very important. Okay, you can see that over here. Let's say for vertex A, you can see that one there has a pointer back to where it is in the doubly linked list. So this one here corresponds to exactly this attribute right here. All right, right here. Versus when I also got, let's say, this particular edge also point back to its position in the list of edges. And that one there also corresponds to this particular attributes. So this will be some programming detail you want to pay attention to when you see the assignments. Okay? And then we got things like, oh, give me 1 minute and then I'm done. Almost done. Okay? And then we also got this reference here is origin. And this one here is destination. Okay, destination. Okay, how do I see that? For example, you can see edge O here, A and B. So here, it doesn't really matter because it's undirected. I can say this one is origin and this is destination. Doesn't really matter. Okay? Or I can say this is origin and that's destination. Okay? So based on this visualization, take a look at the fragment of code in the slides, and then when I release the assignment on Tuesday morning, so please use this as a reference point and then try to get yourself familiar about the implementation strategy. So we'll try to implement some basic functionality for the graph, adding vertices, adding edges, removing vertices, removing edges, or maybe find a path, etc. That's something I'll give you. All right? All right, thank you. And I'll reach out to you about the assignments. All right, thank you.